good news for me. I still do want to point out at the picture, and that is where three special rays, any two of them, they are used in order to locate where the image due to the reflection is going to be. And based on situation, we may need all three or just any two. And as far as calling these rays number 1, 2, or 3, or principal ray being parallel to the principal axis, it is going to be reflected to the focal point, one which is colored purple, F ray, which is the focal ray. If any ray that goes to the focal point, this is what we call optical reversibility. If you think about the purple ray sending it backward, it will trace the same path. A ray going through the focal point is going to come out parallel to the principal axis. And finally, part of property of spherical surfaces or even circles, if you need proof, that anything that passes through the center of curvature of the mirror, that ray is going to be reflected back along the diameter of the circle or trace it back on the same path or on itself. So with this reminder, probably the bigger question that we may have is how we can locate the image. And as far as locating the image goes, certainly we are going to use equations, but locating an image can also be done using these rays. While one example is there on the screen, I will very quickly go through yet another example as if the mirror is a concave mirror. And this is where typically you may want to notice that this is just a practice for having. We take as if the rays are coming from left and left. The reflecting surface of the mirror is appropriately either hashed or shaded, so we know what shade the mirror is going to be. I'm going to use an approximate scale so things don't go wayward. And approximate scale is to say as if the focal point is here, and for spherical surfaces, quite likely you remember that the focal length is half the radius of curvature, so the center of curvature is twice the distance from the focal point. And I'm just going to take an object which is actually very close to the mirror. The object can be anywhere. So, as far as process go, we take a ray, we consider every point of this candle or the tree or a person who is standing here. Every point is actually emitting rays, and then these rays are going in all possible direction. We just need 2 out of 3 special rays. So let's take a ray which is coming out parallel to the principal axis, and according to our ideas that this ray is going to be reflected back through the focal point. And this is where you possibly see that I am using a ruler. And as far as that advice goes, if ray diagrams are included for the final, again, please feel free to bring a ruler to draw the image or locate where the image is going to be. So while this first ray is actually very straightforward, the interesting to think about, and that no real ray can be sent to the focal point and yet hitting the mirror. So we pretend as if there is a ray which is coming out, as if it is coming through the focal point. So we take a ray as if you trace it back, it's going through the focal point, and our rules say that this ray is going to come out parallel to the principal axis. We can take a ray that goes to the center of curvature also, but very likely, although freehand using the ruler, very likely you notice that after reflection, these two rays are getting farther and farther away from one another. They are not going to meet at a point, and this is where we actually go back and think about what image formation actually means. And this is where comes the light gathering instrument that we call the eye. Now, our eye may not be this big, but you will hear the reason very soon. But let's think about these rays hitting our eyes, and our eye-brain combination actually sees light rays coming along a straight line path, and that basically is to say that while the rays are not going to exist behind the mirror, we still think as if these rays are coming from behind the mirror. And while I will leave this ray diagram on the screen for future consideration, here comes the part that, as far as these two rays originating goes, they originated from the tip of the arrow, or the top of the tree, or the tip of the candle, whatever it happens to be. And our eye-brain combination actually thinks this is the point where these two rays came from. And the image is going to appear behind the mirror. And this is where you probably do want to notice that as far as the source of the light ray goes, while it is in front of the mirror, the image being behind the mirror, we consider this image to be virtual, and that when we do a ray diagram correctly, it actually is going to tell me how the image is oriented and whether it is bigger than the actual object, whether it is smaller or not. And as far as example of ray diagram goes, one on the screen is with a convex mirror. You notice that the image is behind the mirror. It is going to be a virtual image, but in this one looks like a little smaller than the actual object. So, how can we figure all these things out? And the answer essentially is through what we call the mirror equation. So as far as the mirror equation goes, we specify a few distances first. So you want to be absolutely clear about the object distance, and the object distance in our textbook is labeled as P. It is how far the object is from the pole of the mirror, or the point where the principal axis intersects the mirror, and the image distance is measured from the same point, but it is how far the image is from the mirror itself. That is P and Q. And that's essentially where, as exciting as it is for me to do the derivation, I actually should the answer does involve something that you do want to know about, and the answer does involve the concept that we use rays which are known as paraxial rays, and that as far as the word goes, it may have something in it that says as if you use rays that are parallel to the principal axis or parallel to something, but paraxial rays are rays which are physically, can be at any angle, but physically very, 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 very close to the principal axis. And that is where derivation of this equation involves what we call similar triangles. But we are skipping the derivation part. Rather, we are going to focus on how we can locate the image. So with the object distance and the image distance defined this way, as far as the relationship between object distance and image distance goes, that is what we call the mirror equation. The inverse of the object distance plus inverse of the image distance adds up to the inverse of the focal length of the mirror, and that also is where comes the part that can be determined how big or how small the image is going to be, and the answer is in the word magnification, abbreviated as M. How the image is going to be magnified or reduced is given by negative of the image distance divided by the object distance, d. But this is where, before we start working on this equation, there is something that you do want to be aware of, that for single reflection, for the light rays to exist, this object always have to be in front of the mirror, and that is essentially where comes the sign convention associated with measuring distances. Anything that is in front of the mirror, we consider that distance to be positive. Anything that is behind the mirror, we consider that distance to be negative, because in front of the mirror is the real space, behind the mirror where the rays are not supposed to exist, it is known as virtual space. And that with this sign convention, the object is always going to be in front of the mirror for single reflection, and the image can actually be in front of the mirror or behind the mirror. While both of my examples, one on the screen and one on the chalkboard, the image appears to be behind the mirror. This is where, quite likely, we may want to think about the magnification number. And as far as the magnification number goes, if and when you put it together, hopefully with few examples, we will also see it in both of the pictures, one on the screen earlier and one on the chalkboard up there. The image is behind the mirror, so Q actually is negative. So if and when you think about the magnification expression, negative Q over P, with Q itself is negative, the magnification actually is going to turn out to be a positive quantity. And the positive magnification tells me that the image is virtual. case that we want to use forward and backward whenever there is a need, and I will provide you with example 2. On the other hand, if you look at the picture above, or if you look at the picture on the screen, looks like Q by itself, that is value-wise, I'm not comparing the sign, is less than the value of P. So the ratio Q over P, if it is less than 1 on the screen, if it is less than 1, we should be able to say that the image is smaller. Or if it is more than 1 that is up on the chalkboard, the image is bigger in size compared to the actual object. But beyond that, there is also something else that you are going to notice between these two pictures, that magnification positive not only says that it is going to be a virtual image, magnification, if it is positive, it also tells us that the image is going to be oriented upright compared to how the orientation of the object is. That is, with reference to the principal axis, how the images are going to be. Now, while it is not going to matter or resurface again, but just so you know, this magnification is what we refer to as lateral magnification, and this is the only type of magnification that we are going to notice and or use for both mirrors and lenses. But as opposed to lateral magnification, which is perpendicular to the principal axis, if and when you think about what other kind of magnification could be there, as far as other kind of magnification is concerned, think about an object which is lying along the principal axis, and objects always being source of light. One end is closer to the mirror, the other end is going to be farther from the mirror, meaning that their P's and Q's are different. So they are going to have different Q's because there are different P's for the front end and the back end of the object. That gives us what we call longitudinal magnification. Little bit complicated to express it in terms of P's and Q's, but there are other ways to express it simply. In any case, we are not dealing with longitudinal magnification. As far as the mirror equation goes, it is very simple and straightforward, and you actually have seen equations of this form before. That is, if you remember adding resistors in parallel or adding capacitors in series. So I will also use the mirror equation to have some algebraic fun to start with. And as far as the algebraic fun goes, the next version is not going to be provided to you. The basic mirror equation is going to be given or provided during quizzes and final exam. But the next version essentially is, because we are always interested in locating where the image is going to be, simplifying the mirror equation always gives us a standard expression for Q as object distance multiplied by focal length divided by focal length minus the object distance. And you probably have seen something like this with the resistors being done before, but here with the interest being locating the image, consider a mirror which is a convex mirror, and by default and convention, convex mirror, the focal length is always a negative number because it really does not converge the rays to a point in front of the mirror. So if and when you think about the image, where the image is going to be, keep in mind that the object always has to be in front of the mirror. This is where, just thinking part, P is always a positive number, F is negative in the numerator, and F is negative in the denominator. You are going to notice, doesn't matter what kind of or what focal length of convex mirror we pick, the image is always going to be a virtual image. Kind of examples that you have seen through pictures 2 or 3 between Monday and today, that the image is always going to be negative, which is to say that it is always going to be a virtual image. There is something more that we can do, and it is with the magnification expression on left, take the P from the right hand side, and for the same convex mirror, bring it to the left, and I will also add a negative sign to both sides. And if you do this algebra, you probably are going to notice that the left hand side is the magnification. So we think again, F is a negative number, cancels this negative, and F is a negative number, E is positive. Right? So, well, maybe I will take you through the journey after all, because without catching this, we are not going to be able to apply it correctly. I still am not going to provide you with this, but mirror equation, take it to the other side, you will find P minus F in the numerator and F times P in the denominator to be equal to 1 over Q, or Q is equal to, the numerator part is fine, but the denominator is P minus F. So, if you are going to memorize it, do it correctly. Again, I will not provide you with, there are reasons behind it, and the reason certainly is, oops, sorry, this one is correct. The reason certainly is, when we have combination of mirrors, we actually cannot apply this simple equation to locate where the image is going to be. But as far as the first argument goes, it still is going to be valid. F is a negative number, P is a positive number, F is a negative number, so the denominator is positive, and the Q still is negative, and it is going to be a virtual. On the other hand, magnification, F is a negative number, and P minus a negative number, the denominator is positive, F is a negative number, the magnification will turn out to be a positive number. Now, as far as positive number goes, one thing that we should actually start to notice is that magnification positive means that the image is going to be oriented upright. On the other hand, if and when you look at it very carefully, we are just comparing number f divided by something which is more than f. The magnification is not only going to be positive, it is also going to be a number which is less than 1. And certainly it means that the image is going to be smaller. We probably don't need to do algebra to understand that in order to put makeup or shaving or even use in the dentist's office where we want to see objects look bigger for more detail, we should not be using convex mirrors at all. Right? Because after all, they are going to give us images. Doesn't matter what the focal length is, images which are smaller. So while the algebra is to say that, look, there are signatures and general results irrespective of what the focal lengths are, we can actually use these information for solving problems. While this is one specific case, another case that I can also refer to just because I used the ray diagram. For a concave mirror, the focal length is a positive number by convention, and we can ask that if I have an object in front of the mirror, we can ask when is the image virtual? That is, actually asking when is Q going to be negative, Q being the image distance. So think about the simplified version of the Q expression. F is positive, P is positive. The only way Q can be a negative number is when the denominator is negative or when the object is inside the focal point. So if you think about it, the very first picture of the ray diagram that I have drawn, purposefully I took the object to be within the focal point, and the image appears to be not only virtual but bigger also. And that basically is to say, just because I said putting makeups or shaving or looking at the teeth, we probably want to use a concave mirror, and that we want to put the object within the focal length of the mirror. Now these being just examples, quite likely the other algebraic thing that you may want to ask, we are talking about curved mirrors. Why not the plane mirror? As far as plane mirrors go, I don't want to trouble you with algebra. On the other hand, for a plane mirror, if you think about how curved it is, it's really curved, and that its curvature is 0. I can say that I don't want to bother you with algebra or relationship, but curvature is determined by inverse of the radius, and the plane mirror do not curve essentially means its curvature is 0 or the radius of curvature is infinite. And that's basically is where the focal length is also infinite, meaning that the plane mirror actually cannot focus rays or gather rays at all. If all parallel rays are coming in, they are going to reflect back out parallel to themselves. But this actually leads to something very interesting for plane mirrors, and that is following the mirror equation. Let me write it the other way. The plane mirror is always going to give you the image to be at the same distance behind the mirror as the object is in front of the mirror. And while it is again algebra, you probably are going to find the magnification to be equal to 1. Possibly the reason that we have not screened this morning when we looked at the mirror, if you did, that, oh, we have the same shape and size. Although the magnification is 1, still the positive sign tells me that the image actually is virtual, as much behind the mirror as I am in front of the mirror. And along with that, again, comment that probably you just want to keep in mind. While the plane mirrors do not magnify objects, that is, increase or decrease their size, there is a left and right hand inversion when we think about the images. But for the most part, it is not something that the text deals with, and we are also going to not worry about the left-right inversion due to plane mirror reflection. Now, this being the topic of reflection, probably algebra-wise, I can point at many things from simple to complex. And this is number 2 in chapter 23. You stand in front of a flat mirror and you are focusing the camera at your image. If the camera is set to focus at a distance of 3 meters, how far are you from the mirror? All that we need to know is that your image is at the same distance behind the mirror as you are, and you have a camera which is focused at 3 meters sharply. So here is the distance between the object and the image to be 3 meters. So we should be able to say that this is 1.5 meters. But it does come with an assumption, although it is not listed in the problem itself. The assumption certainly is that you are holding the camera exactly where your eye is or at the object itself. If you, nowadays, since we all take selfies or holding cameras up in the crowd, if you have the camera at a different distance, then you need to know that. The assumption certainly is something that we can work with, but simple geometry. On the other hand, problem number 9, and as we take a look at word problems, sometimes pictures may be given to you, maybe not, but typically I am always going to advise, you don't have to be to scale, but if you can actually draw a little schematic, it might help you in understanding the problem and also making sense to say that things that we need, we probably should gather. The focal length is given. Radius of curvature 40. Focal length is going to be half of that. And I am also going to advise, as soon as you read the word concave, you may want to think, oh, this is a positive number. We are given the image distance, and that Q is equal to 20 centimeters. And that is where we have some clue. As far as the clue goes, the image actually is virtual. So going with the sign convention, Q actually is negative 20, and having these two numbers probably will allow you to answer the first question, because we are going to use the mirror equation 1 over P plus 1 over Q is 1 over F. So 1 over P is going to be, I'm going to jump forward a little bit, 1 over F minus 1 over minus 20, or 2 over 20, which basically is that P is going to be equal to 10. Didn't use the unit in the equations, everything is in centimeter. So the object position or the location of the distance is 10 centimeters in front of the mirror. Do we expect this to happen? Certainly. And that is where, quick check with knowledges that we have gathered. The object distance is 10, the focal length is 20, so certainly the object is within the focal point. That means that the image is going to be virtual, and then we can actually check what the magnification is going to give us, and magnification being negative Q over P, negative of negative 20 divided by positive 10, and the image is going to be 2 times bigger. So not only 2 times bigger, quite likely we notice that the positive sign is going to tell me the image is oriented the same way as the object itself, which is typically described as upright. And that is where, that is where we continue, and the next one is number 15 as an example. A man is standing at a distance from the shading mirror, produces an inverted image, and we notice that we have to calculate how close the mirror should be stand if he wants to form an upright image of his chin that is twice the actual size. So as far as this problem goes, it is 2 disconnected parts, and if you ask me what is the reason behind the first one, we actually are going to get the focal length out of it, but let's see what the problem actually is asking us to do first, which is actually the second sentence, how close to the mirror should he stand? So as I read it, I should realize it is asking me to calculate the object distance, how close should he stand if he wants to form, and this is where the clues are. Form an upright image which is twice the actual size. So upright and bigger is going to come down the road. Upright certainly tells me that the magnification is going to be positive, and that is where magnification being equal to negative Q over P, it certainly means that Q is going to be negative. Q is going to be negative, so if Q is going to be negative, it makes the magnification number positive. So think about what is written in the problem itself, that the image should be twice the size, so it is going to be 2. So positive for upright and 2 for being twice the size essentially gives us an equation which is negative Q is equal to 2 times P, and we are in a business to determine what P is equal to. So we go to the mirror equation. This is where we realize that we actually need the F. We go to the mirror equation. 1 over P plus 1 over Q is equal to 1 over F. We need P, so it is better to substitute for Q. Q is equal to negative 2P, which is 1 over F. I know it is possibly difficult to see these things as numbers, but first let me simplify this. If you put the negative up here, the result on the left is going to be 1 over 2p. But I mentioned maybe it is difficult to see these as numbers. Since we want the value of p, we can calculate p if I know what f is equal to. Right? Or 2p is going to be equal to f, or p is going to be f over 2. But that is where the first sentence is going to tell us what the f is equal to. So this is in reference to the first part of the first sentence. P is given to us as 1.52 meters. I probably am going to ask you, keep the units uniform. There is no real need to convert everything in meters as long as they are same. And we are given the object distance to be 152 centimeters, and the image that is produced by the mirror has an inverted image 18 centimeters in front of the mirror itself. So please tell me that with these numbers we can calculate what the focal length is going to be. But if you do like doing things on the side and look at the results, we actually do have 1 over f, so no need for this simplification. 1 over f is going to be equal to 1 over 152 plus 1 over 18. And that will give us the answer for how close he should stand with this mirror to produce an image which is twice the size. I think I can, bad word, push one more. And that is with number 47. We have an object 10 centimeter from a concave mirror. produces a real image 8 centimeters from the mirror itself. If the object is moved to a new position 20 centimeters from the mirror, what is the position of the image itself? Now, while doing problems is fun, quite likely you may want to have some backup plan as far as checking whether the answers are going to be correct. So I'm going to spend 30 seconds to tell you that from mirror equation we actually do have some expectation, and the expectation is with the same mirror, inverse of the focal length on the right hand side is a constant. So if you think about it, if the object distance increases, meaning the object moves farther away from the mirror, the image distance actually should go down. And how far down can it go? Well, it can, the least that it can go is actually equal to focal length, which is to say that long time ago, which was one day, we did notice that with concave mirrors, rays which are coming parallel to the principal axis, they converge at the focal point. So as if, in this case, the object is at infinite distance away, and the image is formed exactly at the focal point. And that is basically something that you can see from the mirror equation. But as far as the question goes, it has two parts to it, and that in the first part, the object is 10 centimeters from a concave mirror, so the focal length is positive. So 1 over 10 plus 1 over 8 is 1 over f. And in the second case, the object is moved to a new position 20 centimeters. Where is the image going to be is what we want to calculate. And this is what I was referring in the previous problem, as if you don't want to do things or everything ahead of time, after all, the right hand side is 1 over, this is the second case, 1 over p plus 1 over q is 1 over f. 1 over f is 1 over 10 plus 1 over 8, and being an example that one unknown, one equation, we should be able to calculate what is the position of the image going to be. Odd number problem, before running out of time, you want to take a look at the sign of q to determine whether the image is going to be real or virtual. And along with that, you also are going to look at negative q over p to find out, not part of this question yet, find out what the magnification is going to be. And these are the typical questions that we are going to face. Let's stop here, since everyone is